Hi all, today we will be discussing about revolutionizing VLSI design technology with artificial intelligence. The contents included in this presentation are an introduction about AI in VLSI, and then we will look into what is VLSI design, its design flow, challenges and so on. And then we will look into the involvement of AI techniques in the VLSI design and how this AI driven VLSI evolved. The modern chip design flow of using AI tools are also discussed in the slides. Some other topics discussed are the impacts and benefits of AI in VLSI design and some of the challenges, and also some companies and works related to this field and the future scope of integrating artificial intelligence and VLSI. Very large-scale integration or VLSI is facing a revolutionary change due to the advancement in AI technology. Artificial intelligence now plays a crucial role in VLSI design. Machine learning algorithms made the VLSI design less complex. Before moving into the details of AI-driven VLSI, we will just look into VLSI design and its design flow. VLSI is a branch of electronics that deals with the design and manufacturing of ICs. It plays an important part in developing modern electronic devices. It is an important part of the semiconductor technology as well. If we look into the design flow of VLSI design, it can be divided into mainly four parts: the logic design, logic synthesis, physical design and fabrication part. The logic design falls under the front-end design, while the other three are part of the back-end design. The logic design part includes design specification, architectural design, behavior level design and verification. The logic synthesis part includes netlist, which includes the DFT insertion and formal verification. In physical design part, floor planning and placement, routing, clock tree synthesis and timing analysis, layout verification and sign-off. And the last part, the fabrication part, includes lithography, mark verification, packaging and testing, chip design, post-silicon validation and so on. Now we will look into the drawbacks of VLSI design. We know it is a complex and challenging field. The major challenges are design complexity. Design complexity is a major challenge as the number of transistors and other electronic components are increasing, which causes trouble in flow planning and routing. Another major concern is the power consumption. Designers must balance power efficiency and performance of the chip simultaneously. For timing closure, the design must ensure all signals meet their timing constraint, which is a complex task. Heat dissipation. Efficient thermal management is required as the chip becomes powerful to prevent overheating and other consequences. Mixed signal design. Combining analog and digital signal in single chip is challenging. Issues like noise, interference, etc. may arise. The involvement of AI in VLSI can help to overcome the challenges to an extent. So, we will look into the improvement in VLSI due to AI in the coming slides. As I already mentioned, AI has brought a revolutionary change in the field of VLSI design. Many techniques including machine learning algorithms are applied to perform tasks like optimization, placement, routing, verification, etc. The involvement of AI in VLSI improved the efficiency and accuracy of products and reduced the amount of labor and time. AI also allowed fault detection. The major benefit is its ability to analyze a vast amount of data. Before going deeply into the involvement of AI in VLSI, we will look briefly into what is artificial intelligence and machine learning. AI, the short for artificial intelligence, it refers to the machines that perform tasks that require human intelligence. Machine learning is a subset of artificial intelligence. It is used to analyze vast amount of data. Machine learning algorithms are mostly used to implement artificial intelligence techniques. Now let me give you a brief idea about the VLSI design. The idea of integrated circuits emerged in the late 1950s and 60s. Early ICs contained only a small number of transistors, around tens to hundreds. In 1970, VLSI technology emerged with the aim of integrating thousands of transistors onto a single chip. The development of MOS technology, particularly CMOS, contributed to the growth of VLSI by reducing power consumption and increasing noise immunity. In the year 1971, the Intel 4004 was created, marking the birth of the first microprocessor. During the subsequent years, VLSI design tools such as layout editors and simulation softwares continued to develop. In 1980s, the complexity of VLSI design increased, leading to the development of tools like CAD. This era also saw the introduction of RISC and ASICs and the use of AI tools for design assistance. In 1990s, there was a significant advancement in the technology with the introduction of SOC, deep submicron technology and FPGA. The usage of AI tools like symbolic reasoning systems began to rise during this period. In the year 2000, there was an introduction of semiconductor technology and AI techniques such as machine learning and pattern recognition. Research during 2000 and 2010 led to the development of AI techniques including neural networks, support vector machines, and decision tree. In the year 2010, AI-driven automation accelerated tasks in the VLSI design. From 2010 to 2020, the development of AI-driven VLSI was introduction of ASIC customization, semiconductor manufacturing, and mixed signal design. In the year 2020, real-time adaptation for dynamic chip behavior was introduced. Since 2020, there have been ongoing research efforts to combine AI and VLSI. Now let's look into the modern chip design flow using AI tools. In the given block diagram, we have the VLSI design flow which we already mentioned. The diagram also gives us an idea about some of the proposed AI techniques and for each process. The AI or ML techniques proposed are mentioned here. The first one is for modeling. Some of the techniques used for modeling are linear regression, MAS, GPR, Bayesian network, and deep neural networks. Linear regression can be used for estimating model parameters. It simplifies the process. MAS is useful for modeling complex relationship between design parameters and performance metrics. GPR is effective when modeling performance under varying conditions. It deals with noisy data. For prediction, linear regression, neural networks, GBM, hierarchical clustering, and linear regression, etc. can be used. These techniques can learn from historical design to make prediction about the new design. For fault detection, the mentioned techniques can be useful for both fault detection and classification. They can identify normal and faulty behavior. Especially CNN can analyze graphical representations of data. The combination of CNN and SVM can also enhance fault detection easily. For optimization, there are a good number of AI techniques that can be used for optimization. Some of them were already mentioned. Techniques like RL optimize by learning the best action to take in a dynamic environment. Deep neural networks can be used for design exploration. Huddle binomial model is used for dealing with discrete optimization problem. K-means can be used to group similar designs together. For image processing and layout generation, the image processing includes image classification, object detection, segmentation, etc., which can be done by CNN, GAN, etc. For layout generation, techniques like RL, NN, etc. are used. For pattern and layout recognition, K-nearest neighbor is used for recognizing pattern within the FPGA design. K-means can be used to group the similar data as we already mentioned. For classification, these techniques were already mentioned in the fault detection. It has the same function in classification purpose also. An autoencoder is used for dimensionality reduction. For real-time processing, spiking NN is used, and Bayesian network, graph convolutional networks, etc. are used for analysis purpose. The diagram also mentions some CAD tools used. We will look into them in detail. Synopsis VCS. VCS is high performance digital simulation tool primarily used for simulating and verifying digital designs described in hardware description languages like Verilog and VHDL. MG Questa Sim or Model Sim. It is used for the simulation and debugging of digital and mixed signal designs. Xilinx, Vivado and ISC. They are used for designing and programming FPGAs and complex digital systems. Cadence Virtuoso. It is used for custom IC design and layout. iCaris Verilog. It is an open source simulator for the Verilog hardware description language. It allows designers to write and simulate digital design described in Verilog. Verilator. It is a tool that converts Verilog code into efficient C++ or system C code for high-speed simulation and verification of digital designs. Chip Vault. It is used to help the semiconductor companies manage their intellectual property and semiconductor design data effectively. Synopsys Design Compiler. It is an industry standard RTL synthesis tool used in the digital design. It takes RTL description and synthesizes them into a gate level representation. MG Leonardo Spectrum. It is used for the application specific integrated circuits physical design. Cadence Innovus. It is used for physical implementation and optimization of digital integrated circuits. MG Olympus SoC. They are used for design and development of complex SoCs, which are integrated circuits that combine various components. Alliance. It is an open source EDA suite that offers a wide range of tools for digital and analog integrated circuit designs. Magic. Magic is an open source VLSI layout tool primarily used for designing and editing layout of integrated circuits. Electric is an open source VLSI design system that includes a variety of tools for IC design. Spyglass DFT. DFT analysis tool used for RTL analysis and optimization of digital design to enhance testability. MG DFT Advisor. It is a DFT planning tool used for early stage DFT analysis and planning. Synopsys Tetramax. It is an automatic test pattern generation tool used for generating test patterns that will be applied during manufacturing to detect and diagnose manufacturing defects in ICs. Now we will see the impacts of AI in VLSI. AI has a significant impact on VLSI design. Most of them are positive impacts which improve the efficiency and quality of product. Let us look into it in details. Design automation. Automation reduces the time and labor required by VLSI design process, and machine learning enhanced design automation tools that can optimize layout, placement and routing. This helps designers to concentrate on other tasks apart from design activities. Design automation also increases the chip performance. The second one is enhanced chip speed and throughput. AI can help in design of more efficient chip architecture. Machine learning algorithms can analyze specific tasks and optimize the chip design to meet those applications. AI can also implement parallel processing, which helps in faster execution. Pattern recognition. Deep neural networks can be used for this purpose. These networks have the capacity to analyze various design patterns and process large amount of data. This helps to identify defects in structure and take automated actions. EDA tool enhancement. AI can enhance EDA tools used in the VLSI design. These AI-powered tools can suggest design improvement, detect potential issues, and provide real-time feedback. Design closure. AI is helpful in meeting the design closure, particularly time and power closure. Machine learning can analyze critical paths, optimize clock networks, and perform power analysis. Energy efficient performance. Energy efficiency is a very important factor in today's world, as we are facing so many environmental issues. AI emphasizes energy efficiency along with optimization. Machine learning models suggest design options that balance power efficiency and performance. Customization and personalization. AI contributes in the development of ASICs. AI provides tailored solutions for specific application. It offers the potential to create highly specialized and efficient solutions for a wide range of applications. Verification and testing. AI tools can identify the potential design flaws in less time and effort. Effort required is also reduced. Routing and placement. AI optimized routing and placement to minimize delay and power consumption. AI can optimize placement to reduce wire length and can automatically generate efficient routing solutions to improve performance. To summarize the impacts of AI in VLSI, it has improved performance, speed and throughput, power efficiency, reduced design time, advanced manufacturing, fault tolerance, analog and mixed signal design, continuous learning, and real-time adaptation. As AI-driven VLSI is a developing field, it has many problems to which solutions are not applied. Some of them are data volume and quality. VLSI design has a vast amount of data to be analyzed. Managing and processing this data is a challenging job for AI. Ensuring high quality data is also difficult. Algorithm development. Another major challenge is algorithm development. It is challenging because it requires domain expertise with a deep understanding of VLSI applications. The difficulty faced is to fill the gap between AI experts and VLSI experts. Cost. Even though using AI in VLSI reduces the time and effort, the cost of implementing AI for VLSI application is high. Another challenge is error handling. Error prediction can have serious consequences in design, leading to defects in chip design and manufacturing. Implementation of efficient error handling mechanism is required. Skill gap. Training people with domain knowledge and AI application is another challenge. The gap between AI experts and VLSI experts should be reduced. Model generalization. AI tools trained with specific knowledge may not be able to analyze new design process. The AI techniques are advancing day to day, which may bring solution to the challenges mentioned. The implementation of AI have more benefits compared to the challenges, which also increase its future scope. Here are some companies and works related to AI-driven VLSI. The major companies working in the field of integrating VLSI and AI are Google. The Google's AI research division has been working on techniques such as reinforcement learning and neural networks for chip design. Intel. Intel is investing in AI for VLSI to accelerate the development of semiconductor process. Nvidia. They are using AI to design more efficient GPUs and accelerators. Cadence Design Systems have been incorporating AI into their EDA tools to enhance the design process. Synopsys, they are also working similar to Cadence. Siemens EDA, they are working on integrating AI into their EDA tools to help semiconductor companies design more advanced and efficient chips. Some ongoing research in the field of AI-driven VLSI are neural architecture search. It is a technique for optimizing the architecture of VLSI circuits. Researchers are developing algorithms that use reinforcement learning and evolutionary strategies to automatically design and fine-tune hardware components. AI-based verification and testing. Machine learning algorithms are used to predict potential issues and suggest optimization in design phase. Hardware security. Machine learning models are being developed to identify patterns and anomalies in chip behavior that may indicate security threats. Custom hardware accelerators. Companies are developing specially designed for hardware for AI workloads. The advancement in ML, deep learning algorithms, neural networks will bring revolutionary change in VLSI technology. As AI reduces the time and manual labor, it helps designers focus on new innovations. The growth of AI will result in fast and efficient chip design. AI will continue to be a driving force in VLSI design, revolutionizing the whole process. To conclude, AI has the potential to revolutionize the VLSI design technology. It is an evolving field which is expected to grow and bring positive impacts. The future of VLSI looks promising with the integration of AI. Thank you.